of the joint IISc-TIFR webinar series in chemical sciences. So we are very glad that we have Professor Latha Venkatraman joining us on a very, very early morning from New York. The joint IISc-TIFR webinar series in chemical sciences. Okay. So I just wanted to give you a brief idea of what this entire webinar series really represents. To both Satish, Professor Satish Patil at Indian Institute of Science, Bangalore, and me, we actually have had a lot of collaborative work, but we have realized that, through the scholarship of students and the requisite PIs and research teams do come from a very, very nuanced understanding of the research literature throughout, right? And it becomes increasingly difficult to follow the fundamentals and conceptual development and evolution of the field when there's a lot of literature surrounding you and the students become increasingly confused of what is to be followed. And for this very reason, we conceived about this idea that since we are able to get international experts nowadays online through a very nice Zoom platform, why don't we put together a series in chemistry, which is experimentally heavy, to get the experts speak about the fields, the development of a field. And we are very lucky. We had Frank Spano from Temple University last month, and this time in the molecular electronics field, we have a leader with us, Professor Latha Venkatraman, who's going to share her part of the excitement in this emerging field. I would like to also state that this particular concept has been picked up very well, both from Indian Institute of Science faculty, across all departments in chemistry, as well as TIFR Department of Chemical Sciences. Both the chairpersons in both the departments have been very supportive of this particular endeavor. It hopes to bring together the ISC and TIFR faculty and students through this kind of a program. ACS was wonderful in giving us a chance to support this. So we would like to really thank ACS and ACS Science Talks branding for making this talk possible through Zoom platform, as well as advertising it through their websites. And also I would like to thank TIFR, especially Dr. Satyanarayan, who actually helped us set this live streaming YouTube live streaming thing from the TIFR YouTube channel. With that, I would like to hand over to Professor Satish Patil, who will formally introduce today's speaker, Professor Latha Venkatraman.
Okay, thank you, JD, for this brief background about this webinar series. So indeed, it's my great honor and pleasure to introduce Professor Latha Venkatraman. Latha is more Bangalorean, as many of us are today living in Bangalore. So she graduated from the Valley School in Bangalore, and she moved to MIT for her undergraduate studies in physics in the year 1993. Her thesis work was, undergraduate thesis work was she did with a very celebrated physicist, Professor Dresselhaus, calculating the phonon modes of the carbon nanotube. Then she moved to Harvard to obtain her PhD in the year 1999. And subsequently, she joined Columbia in 2003 as a research scientist. So she started her independent career as an assistant professor in the Department of Applied Physics and Applied Mathematics in Columbia in 2007, and was promoted to associate professor with a tenure in 2012 and professor in 2016. So Latha's research group is primarily looking at the transport in a single molecule. And so she did some remarkably fundamental experiment how the charge transport happens in a single molecule, essentially injecting a charges in a single molecule and putting in two electrodes. So because of these are very fundamental experiments, she has been honored with many very academic awards and rewards. So she's a fellow of American Physical Society in 2016, Alpert Foundation Fellowship in Chemistry, Packard Fellowship for Science and Engineering, and NSF Career Award in 2008. So with this brief introduction, I request Latha to give her seminar. Thank you.
Thank you very much. You can still hear me and everything is okay,
sure.
Technology-wise? Okay.
Yeah. Okay.
I had one quick question. Can the students actually ask me questions, or they can only view?
They can definitely ask you questions. If we get the questions on the chat box, we can make them talk to you as well.
Okay. So to everyone watching, if you do have questions and you want to interrupt, I'm more than happy to take questions. So please don't be shy. I don't have any agenda that I have to get through all my slides. And so I would rather explain something carefully if people are interested. Okay, so I'm going to tell you about a topic that's very interesting for me because it combines physics and chemistry, and this has to do with how you can see quantum interference when you measure transport through single molecule junctions. So before getting into all of this, let me give you a brief introduction of molecular electronics. So this whole field is called molecular electronics. And the motivation, I would say, maybe 20, 30 years ago was really to develop the next generation electronics with molecular building blocks. And the reasoning was that, devices and integrated circuits are all going to be large, and therefore we can shrink the size using molecules. So if we follow how the electronics industry has scaled things, so the first transistor was developed in Bell Labs, and it was about 1/2 inch in size. So that's actually pretty large. And then the first integrated circuit was made by Texas Instruments in 1958. But then if you zoom forward to 2010, the background image here is the Intel Core i7 from 2010, and it already has 1 billion transistors that fit into a 1 centimeter by 1 centimeter chip. And so clearly going from 1/2 inch size for one transistor to 1 billion transistors in a 1 centimeter chip, that's incredible amount of scaling. And then you fast forward again to 2015, which is still in the past, IBM developed a 7 nanometer device. 7 nanometers is actually the size between the source and the drain, so it's not exactly the size of the transistor, but that's still incredibly small. And so if we compare this to the scale of a molecule, here I'm showing a bipyridine molecule. This is 1 nanometer, this is 7 nanometers. You can't gain much by scaling anymore. And so the idea that molecular electronics is going to win because it is smaller is no longer a really important thing. And I will get back to this point at the very end of my talk. And so why would we want to do molecular electronics? Because you can't gain by scaling. So the ultimate in miniaturization, I would say, is no longer a valid argument for doing this. But there's a lot we can do with chemistry that you cannot do simply with a transistor. And so getting functionality out of chemistry, so you can design a molecule that may be a light emitter, or you can design a molecule that has conformational degrees of freedom. And these kinds of things you can only do with molecules, you cannot do with a standard transistor made out of silicon. There's also potential for novel switching mechanisms. So a transistor, again, it's just basically a tap that controls the flow of water in the pipe. You close the tap or you open the tap, and that's all that the transistor does. But maybe we can make more interesting types of devices or circuits, elements, using chemistry. So that's sort of a better motivation. But primarily what we want to do in my lab is really understand how things work. So each time we figure out something new, that's the most exciting thing. And so just to give you some motivation of what we can learn, what are the new things we can get from these types of measurements that we do, we can look at the electronic structure at the metal molecule interface. So this is something that's very tricky to do by any theory. And the reason is that the theory that's used to describe molecules can be done accurately, but the same level of theory cannot describe a metal. And the theory that's used to describe a metal is often not adequate to describe a molecule. And just if you think about it, a metal, we think about it as many atoms, we look at the band structure, etc. Whereas a molecule, you think about it as molecular orbitals. And the two, if you want to mix them together, you have problems. You don't get accurate results. And so a simple example is if I put a molecule next to a metal surface and there's some interaction, so there's some charge transfer, some hybridization of the orbitals, etc. We don't know accurately what happens to the molecular HOMO and LUMO as soon as we put it next to a metal Fermi level. Things shift, and it's not exactly clear how they shift, and it can't be predicted exactly yet, theoretically. There's also other interesting things you can do with molecules and by measuring transport. For example, you can use chemical design to determine whether you're going to have hole transport or electron transport. And again, with silicon, you have to dope it with p-dope it or n-dope your silicon in order to make it a hole conductor or electron conductor. With a molecule, you can just, for example, if you take the thiophene, you simply put the oxygen groups on the sulfur and you end up with an electron transporter versus a hole transporter. So those kinds of tricks you can do with chemistry, but it's harder to do with silicon devices. And again, this is what we can study using single molecule electronics. A new area for my group and my research, and this is extremely exciting, is really applying physical intuition to chemical problems. And this, again, is something we can study using single molecule devices. And I'm not going to talk about exactly this paper, but what we can do and think about is the following. If I have an electrode and I apply a voltage between two leads, and then I have an electric field. As soon as I apply a voltage, I have an electric field in this entire environment. If I put molecules in an electric field, what happens is I can polarize the molecule. And if you polarize a molecule, you can sometimes create systems where a transition is stabilized in the electric field. So a simple example is if you go from this cumulene cis version to a trans version, these are two different conformations. To go from one to the other, you really have to rotate across this bond. And when you rotate across the bond, the transition state is, it's either two radicals or it's zwitterionic. So you have a plus charge on one side, a negative charge on one side. The negative and positive charge system is then going to be stabilized if you do the experiment in an electric field. And therefore, in an electric field, what you can do is convert cis to trans much more easily than you would without the electric field. And so that's sort of the type of problem that we want to address. We have a new center to do this, actually. And this is something that is actually very exciting for us.
Latha, sorry, a quick question. Did the directionality matter for the field, where you put the field across?
No, so this particular experiment is not happening in the junction. It's not doing one molecule at a time. It's everywhere between the tip and the substrate where I have the electric field in solution. That's where the reaction happens. And so we're trying to see whether we can use this electric field driven catalysis to do more interesting chemistry. Isomerization is not an interesting, not a very interesting chemistry problem, but you can do a lot of other, we hope, in our center, we're hoping that we can discover new reactions or new selectivities that can happen just with electric field. Okay, so this is our motivation. What can we do that's interesting using this technique. And so the outline for my talk today is I'm going to first tell you how we do these measurements. And then I'm going to tell you how you want to think about what we measure. So when we measure conductance, what is it that we mean? And how does that conductance relate to molecular structure? And then I'll give you two examples. Again, the focus is on destructive interference. So I'll give you an example where we make an insulator using destructive interference, and an example where we make a switch using destructive interference. Okay, so how do we measure conductance across a molecular circuit? So first of all, what are the components? We have an organic backbone, we have a chemical linker, and then we have the electrodes. So these are the three pieces that put together to give us our system. When we do this measurement, we need to be able to have a clear molecular signature, and we need to be able to do this repeatedly to convince ourselves that we're really measuring this, because there's no way to image this device. So what are the methods used for single molecule measurements? So the most popular, in my opinion, is again the idea that you can start with a wire, you break the wire in an environment of the molecule, and just before the entire system breaks, you can trap a molecule between the two electrodes. And as you see here, there's actually many molecules in this environment and only one is attached, right? And so this idea of breaking wires in an environment of molecules is really what everyone is doing these days. So you can do this also and trap very small molecules. So here people trapped hydrogen using platinum electrodes, or you can trap larger molecules. You can break, instead of just simply pulling on the wire, you can break it by using electricity. You drive current to break the wire. You can do this also in an STM junction. So this is exactly what my lab uses. And so I will tell you in detail about this particular measurement technique. But the simple idea is really you have a tip and a substrate. So I have this gold tip, which is a hand cut with a wire cutter. And then we have this gold substrate. This is gold on mica. We evaporate the gold on mica, and then we drive the tip in and out of contact with the substrate. So the tip literally goes up and down, up and down, up and down. The technique is really versatile. So we can measure conductance, current voltage curves, thermal power, forces, electrochemical effects, photoconduction, whatever we want, we can measure. We just need to couple an extra, if we're doing thermal power, we need to be able to heat it. If we're doing forces, the tip has to be a cantilever, and so on. You can very easily collect 10,000 traces of this in this measurement, and so statistics is not a problem. You do measurements under ambient conditions, so in terms of doing chemistry and looking for reactions, this is an ideal system. And we work in a solution environment. Again, that's an ideal system. This is not ultra-high vacuum 4 Kelvin work. Okay, so what do we measure when we do this measurement? So we first smash our tip into the substrate. So this is a gold contact, and then we start pulling it. And what you see is you have these steps, and these steps are really the gold contact. And we're measuring everything in units of 2e²/h. And so you see these nice steps. Why do we see nice steps? So that's sort of the first question you might have. And so if we look at conductance, the macro scale is very different from the nanoscale. So in a macroscopic conductor, if you've done Ohm's law, you know that current divided by voltage, which is conductance, is proportional to 1/length. So the longer your wire, the lower the conductance. And the reason the longer the wire, the lower the conductance is that your electron is sort of bouncing around, scattering off defects within the wire. It's a diffusive transport mechanism. So the longer it has to bounce and get to the other side, the harder it's going to be. And all of these scattering events actually give you resistance or inverse of conductance. If I go to a single atom contact, actually transport is not this diffusive transport, it's ballistic. So what does that mean? That means that if the electron enters my wire, it leaves without scattering. And so there's no longer a concept of length. The wire can be as long as you want because it doesn't matter. There's no scattering. So as soon as the electron enters your wire, it can get out and everything goes through, right? So that's really ballistic transport. And I want to stress that even in our molecular junctions, it's ballistic transport that we have. We don't have diffusive transport. And so as long as you have ballistic transport, it's no longer how many scattering events can I have within the wire that describes what the conductance is. It's how many channels do I have? And so if I have gold, I have one channel. If I have platinum, I have 3 channels. And that depends on the chemical nature of the atom. So gold, the outer shell is a 6s electron, and that's all that contributes to transport. And so it's a single channel.
Okay, a quick question.
Yeah.
Latha, a quick question. When you say that the molecules also show, when you in the junction, the molecules also show ballistic transport. Is there a dependence on the length of the molecule, as like how long can you make those molecules so that it still shows ballistic? Because you could have hopping, right? In principle, if
you can get to a hopping regime, but that's a much longer regime. And once you're in a hopping regime, then it's no longer ballistic, of course. Right. Ballistic is basically when you're in the coherent transport regime. And everything that I will say is about coherent transport.
But is there a length scale for that molecular architecture, which I will have to sort of have it in my mind that when I design certain things that it cannot be larger than, say, a few aromatic rings, or is there a length scale?
If you can hold your question to the end of my talk, I will show you an example which completely blew us away. And so I don't want to associate, say 3 nanometers is the limit where you can get coherent transport, and beyond that it's going to be hopping, etc. Because I don't think that you can say definitively this is the regime that you're going to be in, simply based on length.
Yeah, so there is a question in the chat box regarding this. How is the coherence guaranteed across the length of the single molecule junction?
So again, for the electron to interact, so it's not guaranteed in the sense that there is a probability that the electron will interact with the vibrational mode in the molecule, or it will interact with the environmental field and then emit light. And in those cases, it's inelastic transport. So it's scattering off vibrational mode. Let's say it loses a little bit of energy and then gets across. And so it's not guaranteed, but the probability for those kinds of events is actually quite low. So it's in the 1 to 2% regime. And it's the sort of the good and the bad, because as soon as you are in this coherent transport regime, it's hard to probe vibrational modes of your molecule using the electron. Okay, so in this coherent regime, conductance is simply 2e²/h, fundamental constant, times the transmission probability for the electron to go across. And the transmission probability, again, depends on the molecular structure. And it so happens that for gold, this transmission probability for each channel is simply 1 in the energy range that we're interested in. So if I go back to my single atom contact, the transmission probability is 1. I have 2e²/h conductance, and therefore this is G0, 2e²/h. A single atom contact gives me exactly 1 unit of G0 conductance. So when I see this plateau, again, as I pull my junction apart, I'm adding atoms to the chain, but the transmission doesn't change because the length doesn't matter, right? The only thing that matters is how many atoms I have in the cross section. So as you pull it, you get a plateau. And then we break that. And since we do it in a solution of molecules, the molecule can get trapped across this gap. And then I have my molecular plateau that I see here. And then I can keep pulling on it. You see that the molecule rearranges where it is in the junction. And at some point, you cannot pull it anymore and you break your contact. So that is how we measure one single trace. And as I said a few times already, we can do this thousands of times. So this is one particular molecule, terphenyl-diamine. You can make a conductance histogram. So this is wrong. It's one trace that I show here. So this is the histogram of one trace. I add the histogram of every trace, and this is the histogram of 5,000 traces. I can rotate it, and now you can see clear features. So this peak here at 1 unit of 2e²/h is the single atom contact. We see it in almost every trace. And then we have a molecular plateau, and the counts that come from this molecular plateau are at 10 to the minus 3 G0. Okay, so that means the transmission is 10 to the minus 3 in this case for this particular molecule. So what does that mean? That means that 1 in 1,000 electrons that come into the molecule actually get to the other side, right? So it's a probability that the electron goes across.
So
and
Latha,
if only 1 in 1,000, sorry, yeah.
Latha, Satish here. So
Yeah.
I think this is follow-up questions on ballistic transport. There are disorder, like for example, torsional disorder. If you look at 2 biphenyl ring, there is a linkage between a single bond, and
Yes.
they are floppy, and there is indeed vibrations.
Yes.
And those would act as a disorder for this ballistic transport, or
No. So the way you want to think about it is in terms of the time scales.
Mm-hmm.
So if an electron comes in and enters the molecule, it gets through in the femtosecond time scale. So that's the transition time. Okay, it's femto or sub-femtosecond, something like that.
Mm-hmm.
My molecular rotation, the time scales are picosecond time scales.
Okay.
So for this bond to rotate, it's sort of a picosecond time scale. And so every electron that goes through my molecule sees a frozen snapshot, because that's so fast. The molecule doesn't rotate within the time frame that the electron goes across. But then when you measure conductance, the measurement that we are doing is in the microsecond time scale. So we are adding up every electron that comes through, every different geometry of the molecule. So the molecule is rotating, the electrons are going through really fast. Each electron sees one snapshot. But so if the molecule is flat, you're going to get one particular rate. If the molecule is twisted, you're going to get a slightly different transmission probability. And we just add everything. And so we get sort of a time averaged. We are averaging the rotational degrees of freedom, and we're averaging every electron that comes through. So if I could measure one electron coming through at a time, if I could measure current at the femtosecond time scale, I would see the rotation of the molecule. And that would be amazing, except you can only measure current. If you want to measure current at the femtosecond time scale, you have to measure it at the amp level, I think. And so the larger the current, the easier it is to measure fast. The smaller the current, the harder it is to measure fast. So time and measurement of current are unfortunately inversely related. And so given our electronics capability, we are measuring everything in the microsecond time scale. We average everything.
Okay.
So
can I ask a question?
Yes.
Yeah.
This is Sanjay. So what is the width, probably the width of that peak where the molecule is trapped? Is that the different orientation of the molecule, or?
So the width of the peak has to do with constraints imposed on the molecular junction structure by the electrode. So remember I showed you sort of a molecule attached here, for example, right? It's not at the apex of the 2 gold atoms. This junction could have a slightly different conductance than this junction. So as I keep pulling, I am imposing different constraints on my molecular junction structure. And so I see changes. So you can see here that this particular trace is going through multiple different conductances, and that represents the width. And the more flexibility there is in the molecular backbone, the broader this is going to be. And actually, this new paper with one of the molecules that Satish made for us, we can show that you get a very narrow distribution because partly the geometry of the molecule is completely frozen. So there's only one way the molecule can attach in the junction.
So even in this particular case, it's always end-to-end connection between the two.
It's always end-to-end, but you can imagine that there are small changes in the structure of the gold, whether I'm at the add atom is up or down or things like that, that can affect how the junction evolves in time.
Okay. Latha, sorry, there are a splurge of questions and I would like
no problem.
I'd like to read them out. One of them, of course, was about the ballistic transport. There was a discussion point where Ravi Venkatraman wrote that there is a possibility that you can think about the molecular orbital delocalization length scale would be an important.
Yeah, I will get to orbital pictures.
Okay, and there are a couple of questions with regard from the students. Chirag Arora is asking, is the transport of electrons across the molecule also correlated with the nuclear degrees of freedom of the molecule?
So again, you have to think about time scales. Nuclear degrees of freedom are slower movements. Right. And so the electron again sees a frozen geometry when it's going through.
Right.
But
so then carry on. Yeah. And so then Shudipto Maiti is a faculty right here. He's asking, can the wave function of the electron be described then as a traveling wave?
So I will get to the quantum mechanical picture of how to think about this in sort of the second phase of my talk.
Sure. Okay.
There's Shudipto here. Thank you.
Shudipto is here.
Forward to that.
Yeah. Okay. And Tushar is asking why in that single trace graph there is a very steep fall in conductance at a particular displacement.
Yeah, so here, what I imagine, since I cannot see what's happening, is that the junction breaks at some point, and then it finds another gold atom to attach to and reforms, or a different molecule shows up in the junction. And so we do see, especially for longer molecules, we see sometimes that it breaks and then it comes back up after some time. And so there are a variety of junction structures that we can see. Except for the special molecule made by Satish's group, there is one condition where we don't see these kinds of breaks at all. Okay. And that's a unique feature, but most of the time we do see these kinds of breaks.
Okay, fantastic.
And all of that is averaged out when you make a histogram, unfortunately.
Okay. And the last question is from Ravi Kishore. Can the small variations in molecular current be interpreted in terms of conformational heterogeneity?
Yes. So it actually tells us multiple things. So if you analyze, so we can analyze the noise we can take a Fourier transform of the conductance or the current in this regime and look at the different signatures at different time scales. Again, you see a lot of activity in the millisecond time scale. And that's indicative. So the only thing that's moving in the millisecond time scale is really the gold atom. So when we think about gold, we think about this nice pristine structure. But at room temperature, you should think about gold more like the surface of water that's boiling. So the atoms are really moving around a lot. And that motion is at the millisecond time scale. So that contributes also to the noise that you have in this system. So as you cool down, that noise is actually going to go away. So if you go to 77 Kelvin, a lot of that gold motion is frozen, and then the signatures do get cleaner. But it's so much harder to work in vacuum and at low temperature. I love solution measurement.
Yeah. Okay.
I spent 3 years of my PhD time working with leak detectors and liquid helium, measurements, and I said never again.
Okay, carry on.
Okay.
Thanks.
So we can analyze this data in one more way. And the second way we can analyze the data is really to look at the length. How long can I pull a molecular junction? And so in order to do that, what we do is we take this trace, we figure out where the gold contact breaks and where we start to form the molecular junction. And then we align all our traces and we add them one on top of the other and make this two-dimensional map. And so what you see is that this plateau ends up being this broader feature over here. But then we can analyze this feature and look at this length scale, right? And if you imagine, again, going back to the cartoon that I had, the longer the molecule, the higher up in the junction it can start to form a junction, and then the longer your plateau can be. And so this length is actually correlated with the molecular length scale. And that is something that we see. For short molecules, we have very short plateaus. For long molecules, we have very long molecules. Okay, so we can play games with this measurement technique. We can basically measure any molecule that has appropriate linkers. So in this case, we have these amino groups. As long as you put amino groups, you can measure them. So we can do carbon chains, for example, and here we have put S-methyl groups. And you can look at the conductance. So now I have simplified my graph. I'm just showing you the conductance histogram, no traces, etc. And I have a chain that has 4 carbons, okay? So I can do 5 carbon, 6 carbon, 7, 8, even 12 carbon. So this is a whole series of molecular junction measurements that we have done. And you can see here that the conductance decreases with length, okay? And so we can look at this trend versus length, and we see for this chain of carbons that we have a conductance decrease, and then we can fit this data. This is on a semi-logarithmic scale. We get that we have 0.75 per angstrom. So if you increase the backbone length by 1 angstrom, you decay exponentially by e to the power of 0.75, okay? And so that's what this trend means. And this is specific to the molecule that you're measuring. So for example, if we switch and we go to silicon, and we do the same measurement with silicon 1 to silicon 10, you can see that you have a different slope here. So if I change the length of my silicon wire by 0.39, by 1 angstrom, then I have e to the 0.39 minus 0.39 decay. So it's a less steep decay. And this is telling us that the molecular structure actually matters. It's not just the length of the molecule that matters. It matters whether I have silicon versus carbon. So I can also do this with germanium. And interestingly, even though I've gone down the periodic table by 1 more row, the difference between silicon and germanium is not as significant as the difference between carbon and silicon. And so these are sort of interesting chemical trends that we can get simply by doing this measurement.
Yeah, Latha, I had just a question actually. So the beta values, right? I mean, do you see any sensitivity of the beta values to the anchoring groups, right? So amino versus thiols versus...
Yeah, so for these types of chains, we basically get the same beta value, plus or minus, I don't know, 5% or something like that.
Right, so same chain, different anchoring groups, the beta values tend to be within the percentage error. Is that right?
I don't know if it's percentage error, but it's very close. It's primarily dictated by the backbone.
I see. Okay, thanks.
And so we can make things actually worse, get a larger beta value. And for example, if you do silicon, oxygen, silicon, oxygen, silicon. So silicon dioxide glass is a really good insulator. And it turns out that if you look at the molecular level silicon dioxide, you also have this crazy high beta value. And this is literally the largest beta value that we had. And so if you compare this beta value for different systems, siloxanes are really the worst, alkanes, and then silanes, and then germanes. So if you wanted to make molecular wire insulators, siloxane up to now is really the best. And oligophenolines are actually comparable to germanes. Okay, so you can get a little press. Worst 1D conductor is the silicon siloxane molecular wires, etc. But coming to the fundamentals, back to the fundamentals. So what is it that we measure? How does the molecule actually matter? So we can think about a physicist's picture of a molecule, and a molecule from a physics perspective is basically it's a quantum dot. It's a very small structure. And so if I take a quantum dot and I solve the boundary value problem and solve Schrodinger's equation, I can get the energy eigenvalues. So the energy eigenvalue, the ground state has a sinusoidal wave function, and it's basically going to 0 at the end and maximum at the center. So this means my electron is most likely to be found in the center. The first excited state is, again, it's sinusoidal. The probability of finding the electron in the middle is 0. The phase of the wave function flips going from one side to the other. And this is what you get from the quantum mechanics. You can get the third and fourth excited state. For an infinite square well, these energy levels are uniformly spaced. And so that's sort of all that you can do. Now, if you look at a molecule, so you have a lot more control over everything. You have control over what these wave functions are, and it's really not a square well. So for example, if I take this system, so I have double bonds between the carbon atoms, and this is butadiene, I can look at the molecular orbital. So this is, again, the lowest energy orbital. This is the next level, and then the third and the fourth. This is just the pi. I'm only looking at the pi system. So you see a strong similarity between my quantum well idea and this system. This butadiene has 4 electrons in the pi system. And so I have 2 here and 2 here. So these 2 orbitals are going to be occupied, and these 2 orbitals are going to be unoccupied. But what's different between an infinite square well and a molecule is that these energy level spacings are now all different. Okay, so we have a molecule is really a designer quantum well. We can tune the properties and do what we want. We're not limited by this simpler structure. So now you want to think about what happens, how does electron transfer across this nano object, either a molecule or quantum dot? How do we think about it? So I've already hinted at the fact that, electrons will be transmitted across. And so we have to think about transmission probability. So this is an example of a quantum dot that is weakly coupled to the leads, and the electron is incident on one side, and it is transmitted on the other. There's a probability of reflection on one side, etc. And so this is sort of our general picture. Okay, so now I can put my energy levels, and then I have the energy levels for the 2 electrodes, and I have electrons filling up to some Fermi level on both sides. And this is sort of the electronic structure picture that I want to think of. So the transmission probability is going to depend on the energy of the incident electron. So am I transmitting here, or am I transmitting here, or am I transmitting here? Because the energy levels within the dot vary. It's also going to depend on how well coupled my molecular orbital or my quantum dot orbital is to the leads. So those are sort of the 2 parameters that are going to be interesting to us. Now, we can think about this as an optical analogy, because somehow it's much easier to understand what happens in optics, because somehow that's more intuitive.
Latha?
And so, yeah.
Sorry, just a quick question. You're of course assuming it as simple as a sort of a quantum dot, right? Without thinking about the architecture of the dot or how the, you can have. So you are assuming that you are having a continuous wave function across.
No, I'm not assuming anything yet.
Okay.
I'm trying to start from the simplest, and then we'll get more complicated.
Fine.
And so transport across the quantum dot is basically, I have a wave of electrons coming in. It's weakly coupled to the dot. There's some probability it goes across. There's some probability it gets to the other side. It can get reflected here. It can get reflected here, and so on. That is sort of my general model of a molecule and transmission. So I have to think about waves going across two barriers that I have. So what is the optical analogy? You can think about two partially transmitting mirrors. Okay, so that's literally exactly what we have here. I have my light coming in. This mirror is going to reflect some fraction of the light. It's going to transmit some fraction of the light. I hit another mirror. Again, I'm going to have reflection or transmission, and I'm going to get some light coming out. So if I think about this and I say, what is the percentage of light that's going to get transmitted through the cavity, right? So if I have a mirror that's 0.1 transmission probability and another mirror that's 0.1, do I end up with 1%? Okay, so this is sort of the question that you can think about. And people know that it depends on what is the separation between the mirrors and what is the wavelength of light, right? Because that is going to matter a lot. And the reason that is going to matter is that if I have 100% of the light coming, some fraction gets reflected. Again, in here, I get reflections, and then I get reflections again, and this can get transmitted. I can get reflections and so on. So I really have to add up all the possible waves that go through, get reflected, etc., to figure out what is the net transmission on the other side. Okay, so how do I do that? So let's say T is the transmission of the electric field across each mirror, R is the reflection for the electric field, and T squared plus R squared equals 1, so T squared equals 1 minus R squared. Again, this is very simple. I have a light wave coming here, and just looking at the electric field. So the red here is the reflected fraction, and the blue is the transmitted fraction. Because it is light, as it propagates, I'm picking up this phase factor that has to do with the distance that I'm going across. Now this is getting reflected, so I have added this R here. This is the transmitted part, so I've added the T, and then you have this, and it goes on and on. So you can add the series, and when you add the series and you get the intensity of the light, which remember is the square, proportional to the square of the electric field, the intensity has this formula. So what do we want to note here? The intensity depends on this D, the separation between the two mirrors, and it depends on the wavelength, okay? And so we can look at this in slightly more simpler expression. So let's say I take a D of 10 microns. I have a transmission for each mirror of 0.1. And I look at it as a function of wavelength. There are some wavelength where I'm going to have unit transmission. And this is, again, sort of commonly known. This is a standard interferometer. If the gap, the distance between the two mirrors, is some integer multiple of the wavelength, then you can build up a standing wave within the mirror, and then you have unit transmission. And the reason you have unit transmission is that you have destructive interference of all the reflected light. So everything adds up to give you unit transmission, okay? If you increase the transmissivity of each mirror, you get these wider peaks. The transmission probability still goes to 1 exactly when you have that integer. 2 pi d over lambda is exactly n pi. You get this unit transmission. But if you're off resonance, you don't get zero transmission, you get this Lorentzian line shape. So this is exactly a Lorentzian line shape, okay? And so when you have d equals lambda over 2, you set up this standing wave. When you have d is a lambda, you have this standing wave and this standing wave, and so on. And now if you go back to the infinite square well, these look exactly like our energy levels, right? And so when my wavelength matches one of these energy levels, I get unit transmission, and so on. And so, yeah, this is a Lorentzian. And another important part to keep in mind with this mirrors is that the phase of the electric field that goes across, it goes through a phase shift when I go across a resonance, okay? So if I go back here at 644, the transmitted electric field has a different phase than at 646, okay? So that's the other point to keep in mind. Okay, so going back to our molecule and our simplistic picture, we have these two, we have a wave incident here. I have a transmission probability that I need to think about. I'm looking at this whole thing like an interferometer. I have a Lorentzian line shape. The width of this Lorentzian depends on the coupling of my orbital to the leads. And whether I have unit transmission or non-unit transmission depends on whether I hit resonance. And when I hit resonance, that's when the energy level that I'm transmitting across is matched with the energy of the Fermi, okay? And so if you think in terms of a mirror, this sort of all starts to make sense, I think. I don't know if there are any questions about this, because this is sort of very basic, but it's a nice way to think about this. Okay, so when we measure transport, what do? We apply a voltage, right? So that means we move the chemical potential on one side relative to the other. And then what do I have? I have all of these electrons here can get transmitted across. The transmission probability is going to depend on where in this curve energy level diagram I am. So again, you have to think about what is the wavelength of light going across my interferometer. Depending on the wavelength, I'm going to have different transmission probability. And so I add up the transmission probability of all of these electrons, and then I get the net transmission. And so basically, I have to integrate this area under the transmission curve to get the amount of current that I'm going to get. Okay. So, so this is how you want to think about transmission. Each molecular orbital is going to contribute to your transmission curve, and you have to think about the electron as a wave. Destructive and constructive interference are important. So how do we actually work out the mathematics of this? You think about this in terms of a Green's function, and again, you don't have to worry too much about the details, but what I want to highlight is the following. The transmission is really the square. So what we measure, it's like you add electric fields and then you get the total intensity of light. The same thing has to be done with the transmission probability. We have to add the transmission probability for each orbital and then take the magnitude squared to get the total transmission. So if we have multiple orbitals that we are transiting across, we have to consider the phase of each transmitted wave for each orbital, and we have to add the transmission probability for each orbital and then take magnitude squared, okay? So if I have two orbitals, orbital I and orbital J, I add the transmission probability for both of them at the energy that I'm at the energy that I want. I take the magnitude squared, and then I get the total transmission. So if the transmission across orbital I has a different phase relation than the transmission across orbital J, they are going to interfere destructively. If these two orbitals have the same phase relations, then they're going to interfere constructively. Okay, so we have to keep in mind the phase of the electron that's going across my orbital and the energy at which I'm transmitting. Okay, and so if I take one orbital, it's a very simple picture. If I am this side of the resonance, I have one phase relation. If I am that side of the resonance, I have another phase relation. As soon as I take two orbitals, okay, if I'm in above the resonance, I have one phase, but if I'm below the resonance, I have a different phase. And so I have to keep that in mind, okay? So let's just go through the details for this butadiene example. Again, we have 4 orbitals. The electronic wave that's getting transmitted across this one has the same phase relation as the orbital, okay? So the wave that goes across is going to have the same phase at one end where I'm injecting the electron and at the other end where it exits the lead. The electron that goes across the second orbital is going to have a change of phase as it goes across. So I'm starting red and I'm ending blue. Okay, so just for this orbital, because this orbital has 2 different phases at the 2 ends, I have to keep in mind that the electronic phase, the electron that transmits across this orbital is going to have a phase change. I also have to keep in mind whether I am transmitting above energy of this orbital or below, because that's going to give me a second phase shift. So there's these 2 phase relations that you want to keep in mind. So let's look at this one example first. Let's say my electron is going across between the HOMO and the LUMO. So this is the energy of the electron. So I am above the resonance of HOMO -1 and HOMO. So both of these will have the same phase relation. I am below the LUMO and LUMO +1. Again, both will have the same energetic phase relation. However, HOMO and HOMO -1 have opposite phase relations. So HOMO and HOMO -1 will interfere destructively. LUMO and LUMO +1 will interfere destructively. HOMO and LUMO will interfere constructively because in one case I'm above resonance and in the other case I'm below resonance. And HOMO and LUMO have opposite phases. So I have 2 factors of pi, they cancel out. So the net transmission that I see looks like this. And I'm saying that HOMO and LUMO interfere constructively. HOMO -1, HOMO interfere destructively over here. LUMO and LUMO +1 interfere destructively over here, and so on. So every pair of orbitals, you have to figure out what is the net interference that you're going to see, and you add everything up, and then you take magnitude squared, okay? If I change my anchoring point to this one, okay, so instead of injecting here and taking out at 4, if I take out at atom 3, what does that do? So if you see atom 3, it's blue, blue, red, right? So the phase relation as the electron goes in at atom 1 and comes out at atom 3 has changed for LUMO +1. It has changed for LUMO. It's the same for HOMO, and it's the same for HOMO -1, right? If I compare injecting at atom 1 and taking out at atom 3 with injecting at atom 1 and taking out at atom 4, I'm going to have different phase relations. And so again, if I look at transmission at Fermi, and my electron is coming in at this energy, right? HOMO and HOMO -1 are going to interfere destructively because again, this is red-blue, this is red-red. I'm above resonance for both, so these 2 are going to interfere destructively. HOMO and LUMO are going to interfere destructively because this is red-blue, this is red-blue, but in one case I'm above resonance, in the other case I'm below resonance. And so I get a net phase relation of pi, and so HOMO and LUMO are going to interfere destructively. And so you can see already that if I go between, if I simply change the anchoring point, I'm completely changing the transmission because I'm changing how the waves go across my molecule. This is something you cannot do with 2 mirrors. There is no set of 2 mirrors where you can achieve something like this. So that's the beauty of transmission across molecules. Okay, so you can look at this as a picture. There's a really nice, if you look at
just a quick, thing there. I think it's a very beautiful picture that you showed in the last slide, showing how the quantum interference effect works. So just the couple of 2 points here. One is essentially this interference will only work if your couplings between the two orbitals and the electrodes, for example, are roughly the same, and the energies are roughly the same. So you need energy and coupling matching.
Yeah. So if you look at this transmission curve, this is calculated for this molecule. If instead of tunneling at E Fermi, I was tunneling at this energy, I still have the same destructive interference, but the complete cancellation is gone. My transmission is 10 to the minus 2, as opposed to being very low. Okay, so where within this gap I have my electron going across dictates what I measure. Okay, so the energy, so it's, I mean, just like in your interferometer, depending on the wavelength of the incident light, you're going to get either nothing coming out or either unit transmission, right? So the energy scale matters a lot. And yes, in this particular case, the couplings of these terminal atoms to the leads is in this model diagram, it's taken to be the same. Okay, so this is sort of,
sorry, if I may also ask a question, just following up on that comment. These pictures that are there, they have been drawn for an uncharged molecule. They presume, they have been calculated for uncharged molecules. During transport, you actually inject an electron in. Does that become a case to consider?
So
or is there any deviation coming because of that?
You have to think about the mechanism for transport. So this is all a coherent transmission picture, and I am assuming that it's a single electron model. I'm not looking at electron-electron interaction. Now, if I charge my molecule, that means I put an electron in the LUMO, let's say, my molecular orbital structure is going to be changed. I no longer have this neutral system, and that is going to change everything.
So essentially, it's a picture exclusively for the ballistic limit.
It's a picture that's exclusively for ballistic for this neutral molecule. So if I consider a charged molecule, I have to take, I cannot take the neutral molecule transmission curve and simply say, oh, if I'm charged, my Fermi is going to be between LUMO and LUMO plus 1. I cannot say that. Because as soon as we charge a molecule, that means the electron resides on the molecule. So we have to consider nuclear degrees of freedom, how they accommodate for this, how the solvent reorganizes in order to screen out the charge. And we have a different system.
Thank you.
Okay.
Does that make sense? So it's not simply putting an electron in the LUMO, shifting Fermi to this energy because that's my new energy, and then sticking with the same neutral molecule picture. And if you look at the literature, unfortunately, that's what everyone does. They simply say, oh, if I have a charged molecule, I take my neutral molecule picture, I simply shift Fermi to where it should be if I have a charged molecule. So if I have one electron in a LUMO, the next electron will have to go in the same LUMO. That means my Fermi energy is here, because that's the energy required to add an electron. And the energy required to remove an electron, it's the same. And so I just shift Fermi to this and I use the same transmission curve. That's just nonsense, because as soon as, I mean, from a chemistry perspective, as soon as you charge an electron, the nuclear degrees of freedom completely change the system. I might have, it's like a different molecule. So you cannot do that simply shifting of the Fermi level.
Can I just interrupt you, Latha? There are lots of questions in the chat box based on the very nice description just you went through. Let me take the one by one. There was an old question from Shubhra Ranjita, who had asked that, do all atoms show this kind of coherence effect? In the sense, are all the atoms involved?
So all the molecules, so again, it depends on the molecular structure of, I think I have enough material for 2 talks in this.
Yeah, I know. Don't worry about it, Latha. We're very happy with this one talk, and we will go.
No, so I'm just saying, if you want me to give another talk with the second half of my applications of all of this, because I'm less than halfway through, I can do that tomorrow. I know initially you said you wanted 2 talks on Thursday and Friday.
Right.
But I will give an example where all atoms are not involved. Just the next example is that.
Okay. And just carrying on.
Mm-hmm.
So there were questions in terms of, is there an upper limit for the molecular length for a single molecular junction to operate? Again, the same similar question.
Yeah. So that's in my example, and so I don't want to say that there is an upper limit. I'm not convinced that there's
You're
an
not
upper
convinced
limit.
that, yeah. Okay.
I mean, yes, if you think about microns,
yeah.
I think there is an upper limit. But if you look at carbon nanotubes, you can have ballistic transmission for pretty long length.
Very long distance, yes, absolutely. Okay. Ravi Kishore is asking, how does one understand the beta values at the level of the molecule?
Yeah, it's coming.
Okay. Okay. And then Sujit Das, who is a first-year student at TFR, he's asking, how can alkanes be conducting when there is no double bonds for conjugation, right? Is there any insight that you can provide?
Yeah, so you have to do the same thing for a saturated molecule. Molecules again have orbitals, and you have to look at every orbital, and you look at the transmission at the energy that you want. So it's exactly the same thing. You don't need pi electrons.
Yes, that's right.
You can even get unit transmission from an alkane.
Correct.
If your energy alignment were just beautifully aligned.
Right.
Yeah.
Right. That example was beautiful, the optical cavity and the correct correlating to that. Okay. Then Atin is asking, try to measure capacitance of the single molecular junction. And second question, of course, is how do you know it's a single molecule in the junction?
Yeah. So the reason we know it's a single molecule is I showed you the alkane data. And let's say I was measuring, I don't know, 10 molecules, right? The fact that we get this very nice exponential, that would mean that I would be measuring 10 molecules for every one of those lengths. And that is hard to imagine. It's hard to imagine that for a butane, I have a junction that's exactly 10 molecules. And then I have the same thing for a decane or dodecane, right? You would imagine that if I'm measuring n molecules, I should be having some fluctuation going from the shortest junction to the longest junction. Right. So that hints at the fact that we have all the same molecule numbers. So maybe I'm measuring thousands in each case, and I still get this exponential dependence.
Sure.
But occasionally we see a peak for 1 and a peak for 2. So we see a shoulder, and we can fit that with a double Gaussian, and then you can see that there's n and sometimes even 3. And so when we see these multiples, we know for sure that, you know, the main peak is really 1 molecule, because then it can't be 1,000 and 2,000 and 3,000. So those two things together, we are pretty sure. But if you have a broad peak, maybe it could be 1 and 2. Again, if you do measurements at a really dilute limit, you can convince yourself that it's only 1.
Okay. And the related question from YouTube is the full width half max of the peak related to the formation probability of the junction?
The full width at half max is not so much related to the formation probability, but the height of the peak is related to the formation probability.
Okay.
And just to throw out some numbers, if we look at benzene diamine, or if you did a butadiene experiment, the probability might be 25–30% of the junctions have a molecule. By the time we get to biphenyl, so something that's about a nanometer in length, we are at 95% junction formation probability.
Okay.
It's almost impossible to find traces in our measurement that don't have a molecule.
Okay, fantastic. Sandeep Mondal, again from YouTube, why conductance decay exponentially with length if it's ballistic transport?
Yeah, so again, it relates to the molecular orbital picture. And you have to look at, so just, okay, let me go to the next slide, and maybe I can explain a little more about the molecular orbital picture.
Right.
So if we look at benzene, so this will address also the missing atoms, or do every atom contribute? If you take benzene, you have 6 pi electrons, and you can make the molecular orbitals of benzene. So these are the 6 orbitals. Linear combination of 6 orbitals gives you, of 6 atomic orbitals gives you 6 molecular orbitals. You fill in your electrons, so you have 2 occupied here, 2 occupied here, 2 occupied here. Your homo-LUMO gap, this is LUMO, this is HOMO, they're degenerate, and then you have, these are your orbitals. So now if I put leads on this, the first thing that you see is there are 2 orbitals that have no weight at this point. So if there's no weight, that means my orbital, this particular orbital, cannot communicate with the electrons on the lead. And so these 2 should not show up in my transmission picture. There is no way I can inject an electron into this orbital because I'm connecting here, okay? And so that's already, so we see that these 2 atoms don't matter in this particular system. So that leaves me only with 6 orbitals that I have left. And now I can look in detail at the orbitals. So if you look at these blobs, they are sort of drawn to scale. So if you remember, benzene has this bean-shaped orbital. And so if you look at this HOMO -2, the sphere here is small, whereas the HOMO -1, or HOMO, this sphere is larger. So what does that mean? I have more weight on my orbital at the end where I'm coupling to the leads. And so this orbital should couple better than this orbital. And so we should be able to see all of these effects. So going back to the mirror analogy, for this particular resonance, my transmission is larger, my T is larger than for this resonance. Okay, so I have a broader resonance. And the same is true for this one and this one. And then the colors tell me the phase relation. So this and this have the opposite phase relation. And I know if I inject an electron in the middle, one is below resonance, one is above resonance, so I'll get constructive interference, okay? And so this is the transmission. You do the NEGF model. This is the transmission picture that you have for benzene. And you see there are only 4 peaks because those 2 orbitals that have no weight at the ends, those are completely irrelevant for what they have basically 0 transmission. This is Fermi. I have these 2 occupied, these 2 unoccupied. These are the orbitals. And now I can think about this in a matrix form. Okay, so this was really the brain work of 2 of my students, Suman Gunasekaran and Julia Greenwald. They came up with this idea of, let's look at the transmission for every orbital and compare for every pair of orbitals, okay? So that is what we're plotting here as a matrix, okay? So I will walk you through this. So we are analyzing the interference between every 2 pairs of orbitals at every energy. And we can plot this at the Fermi energy. So again, I have 6 orbitals for benzene. I'm just looking at the pi electrons again. It's a simplified picture. If I look at HOMO and LUMO, so I can look at this, do I have, yeah, so I have my orbitals here. If I look at the diagonal terms, these are the contribution of the individual orbitals, and I just add that contribution. So if I only had HOMO, for example, I would get this much transmission. If I had nothing else, if I didn't have to worry about any of the other orbitals. So that's the diagonal, and you see that it's all either white or red. So white is 0 transmission. Red indicates constructive interference or sort of positive transmission. And then I can look at off-diagonal terms. So for example, if I look at this particular square, This tells me, because it's red, it's constructive interference, and it's constructive interference between LUMO and HOMO. Okay, so that's why it's red. So in 1,4-benzene, HOMO and LUMO interfere constructively. This is blue. This means that LUMO and HOMO -2 interfere destructively because it's negative. So if you analyze the LUMO, the phase relation between atom 1 and 4, it's red and red. For HOMO -2, it's blue and blue, so they have the same relative phase difference across the molecule. But HOMO, I'm transmitting, at Fermi energy, I'm transmitting above the HOMO -2 and below the LUMO, so I have that below resonance, above resonance phase shift, and that's why this is blue. And then LUMO +1 and HOMO -1, this is all white. They don't contribute to transmission. Okay, so I have no transmission because these atoms have nothing. So we can analyze every molecule using this type of a picture and really understand for every pair of orbital that we consider what is the interference. So LUMO +2 and HOMO -2 interfere constructively, etc., etc. And this is really nice because now we are able to work in the basis of molecular orbitals and get a complete picture.
Yes,
okay.
That was something that when you started with just a quantum dot, but now you have come across with the entire architecture of the molecule being put together in understanding. Okay, just drawing on from the questions, Chirag Arora. So just like you drew an analogy to the longitudinal modes of an optical cavity to your electron transport problem, I'm curious to know if there is any role of transverse mode or its equivalent in your problem.
So transverse mode is just, what is transverse mode? It's your electric field is in the other direction, right?
Yes.
Yeah, so that's not going to get transmitted in a molecular junction.
Right.
I mean, if I think about the momentum vector of my electron, the momentum vector has to be in the transport direction for it to matter.
Yeah, no, but I think the molecular orbitals are three-dimensional, so we have to consider that part. So
yes,
it's just the representation that you're choosing on this board right now, but
yeah,
really three-dimensional. Okay. The other thing is, Atin is asking, what is the percentage of trace? Okay, so this I think was addressed. What percentage of traces show molecules? I think that's been addressed from the previous data. There's a question. Do you see signatures of a Coulombic blockade?
Yes, we do. But Coulomb blockade, remember what Coulomb blockade is. So if I add one electron, I have to consider electron-electron interaction.
Right.
The energy to add the next electron is blocked because I have to pay the electrostatic cost of adding 2 electrons on my molecule. And again, that goes to, let's say I put 1 electron in the LUMO, the energy required to put the next electron in the LUMO is not the same because you have to pay the Coulomb blockade charge, right? And we do see that. And that is a completely different, again, that picture is no longer coherent transport. It's sort of this hopping mechanism.
Yeah, it has to be hopping, right? Ravi Kishore continues to ask, do you also see tunneling current like in STM without a molecule connecting the electrodes? Of course, right?
Yes, and that's tunneling to vacuum barrier, but that's very low.
Very small. Yeah.
So by the time you get to the gap of a 1 nanometer between the 2 electrodes, we almost have no current.
Right. And then he says, how does this picture change as the position of the Fermi level increases? So I think
so as you tune your Fermi level, if you go up or down, you can see on the transmission curve that my total transmission is going to be different. And that's exactly what you see.
Okay. And Shubhra Ranjita has a clarification on her question. She was asking about all atoms to show. What she meant was the metal part. So she was asking if apart from gold, all other atoms in the periodic will have a similar kind of behavior, or
you can do measurements. I mean, with silver or platinum or other metals.
Other metals.
The general story is the same. The details are slightly different because the work function of gold is going to be different from the work function of silver. Alignment of molecular orbitals to silver is going to be different from gold. So experimentally, you will see differences, but
right.
the concept is going to be the same, the general concept.
Right. And a very quick question, extending benzene to graphene. This is Krishna Priya is asking if a graphene fragment, if put in between electrodes, can it be correlated to the benzene picture?
Definitely, it depends on how big your graphene is and whether you think about it as a band structure or still molecular orbital picture. So if you take a graphene nanoribbon that has, I don't know, 10 benzene rings, you can think about it more as a molecule, and then depending on where you inject, you're going to get destructive or constructive interference.
Right.
If you're much longer, then you're sort of in the band structure picture.
Yeah, the band structure. Okay. And there's a question by Ravinder Kumar who is asking, how do you measure snapback distance?
So the way we measure it is we actually reverse our trajectory and we go back and form a contact, and then we can see how much we had to push the electrodes together to form a contact. And from knowing that, we can figure out what is the snapback.
Okay. Well, the Ravi Kishore adds back and says, can we call this as an orbital mapping in a molecule? Like
for this picture.
Right.
Yeah, so it is basically an orbital mapping. I mean, you have to keep in mind what we measure is the total. We can't go in and measure just this interference. This is how we understand it, but we can't actually measure orbital by orbital interference.
Yeah, that's right. Okay, cool. I think we've just finished the question, so you can carry
on. Okay, so if we can do the same trick and go to a 1,3 connected benzene. The transmission again looks very different, and it's the same idea. You have to look at the phase of the waves, where you're coming in and going out. And so all of the orbitals contribute to transmission, and then we can draw this two-dimensional map. And what you see is that LUMO and HOMO have destructive interference that completely cancels out the constructive interference of HOMO with itself, or the single orbital transmission. And so the net transmission is almost zero, okay? So, and then you can look at LUMO and LUMO +2 and HOMO -2, and again, you see that this is blue. And again, my injection points are this one and that one, okay? And so this is again how you can do an analysis of all the orbitals in the orbital basis, so to speak, and get a much better understanding of why we have this interference, rather than simply saying, oh, quantum interference in molecules. Okay, so really what we want to know is, can we use these concepts and create systems with novel transport properties? So that's sort of what we are getting to. Okay, so I'm now getting to the applications, and I don't know, I just want to check. I have a meeting in half an hour.
Yeah.
And I know, so we were supposed to go for another 5 minutes, correct?
Right. So we can.
What do you want to do?
Yeah. So we can take maybe one example, and then we can conclude the session here. After that, we might have some questions, few more questions based on this slides, and then you should be okay within 15 minutes. You should be done, I guess.
Okay. So I will skip this silicon wire. This is a sigma system, and I was going to explain how you go through a sigma system, which is actually quite different. I will tell you about this newest paper that's supposed to come out on Monday. So it's still on the, actually, is your YouTube video public?
Oh, yeah. Do you want me to close it?
Well, I won't say where it's getting published.
Okay, that's fine. Yeah.
Okay, so destructive interference, when you think about it, it's only used to cancel out transmission. But can we also use it to do more interesting things? So that's sort of the question that we have. So we worked with actually Peter Scarborough's group, and I actually met him in Bangalore at one of the, I forget exactly when this was, but there was a conference in November in Bangalore. That's when I met him. He sent us these series of these molecules. So these are benzothiazole units. There's this BT unit. And then we have fluorine arms. So this is a fluorine, and they've made it with 1, 2, and 3. So, and the measurement was done by Julia Greenwald in my group, and DFT calculations by Tianren Fu, and Suman Gunasekharan added all the destructive interference type understanding. So this is the molecule that I want to tell you about as an example. It will address some of the questions, but not all. So you can look at the molecular orbitals for this system. It's more complicated because I have many more atoms, I have many more orbitals. But if you look at the LUMO, because of this special BT unit, which is electron rich, the LUMO is actually very localized. It has almost no weight at the ends. And so what do we know about LUMO? We know that LUMO is not going to give us a broad transmission peak. It's going to be very narrow in the best case because there's no weight at the end. If there was absolutely no weight at the two ends, we would get zero transmission across LUMO. The HOMO and HOMO -1 are shown here. And if you look at the phase relation, HOMO is blue-blue, HOMO -1, and HOMO is blue-red. So blue-red and blue-blue, and if I inject my electrons between HOMO and LUMO, then HOMO and HOMO -1 are going to interfere destructively because the phase relation, I'm in both cases above resonance, but the phase relation of these two orbitals are opposite, and so they're going to cancel out. What about LUMO and HOMO? Normally, you have constructive interference between HOMO and LUMO because they have opposite phase relations, but then you're in one case below resonance and in one case above resonance. However, because LUMO is localized, it doesn't contribute. So I am canceling out this constructive interference because of this localization, and therefore this destructive interference between HOMO and HOMO -1 is going to dominate my picture, okay? So we can calculate the transmission. This is a DFT calculation, and you can see here, this is the LUMO. It's extremely narrow, okay? So transmission due to LUMO at Fermi is negligible. I mean, you can just think about this as a single level picture. It's just really very narrow. Constructive interference between HOMO and LUMO is therefore minimized. So we don't have this nice, usually round shape that we have because of this narrowness. HOMO and HOMO -1, these are very close in energy, but they interfere destructively. So I get this very steep drop in transmission because of this destructive interference. And so this is again, our orbital picture. These two basically cancel out. So what you end up with is a very low transmission at Fermi. And it's dictated by this destructive interference. Actually, you can't just take destructive interference of these two because HOMO and HOMO -2 interfere constructively. HOMO -3 interfere destructively because all the phase relations and orbitals have to go back and forth. And so you have to include all of these things. And so we can make our, and then what we measure is current, okay? So if you measure current at high bias versus low bias, you can see that at high bias, the area under the transmission curve is going to be very different from the area under the transmission curve at low bias. And that's because I have this very nonlinear transmission, okay? And that's really key. If you want to make any device that's interesting, you need a nonlinear transmission because as you change your energy, you want to see large changes. And so so if we look at this map that I have introduced before, this is, again, this is done for, I forget whether it was for n equals 1, 2, or 3. But you see here, HOMO interferes constructively with HOMO -2 here. This is red. Interferes destructively with HOMO -1 and HOMO -3. So you have this checkerboard pattern of all the occupied orbitals that give you this nice interference picture. LUMO is white. It's out of the picture. We don't have to consider LUMO. LUMO +1 actually interferes constructively with HOMO. LUMO +2 interferes destructively. But again, because you see it's faintly colored, these don't actually matter too much. We are dominated by what we see in this picture. Okay.
Latha, just a quick question here again. This molecule does have conformational flexibility, right? So does the, the relationship between the orbitals, the HOMO -1 actually pan out across the different conformations?
Well, so the conformations are actually somewhat limited. First of all, this is a fluorine, so that's actually quite rigid. And then the rotational degrees of freedom, again, we are averaging everything out. And so the probability of measuring current through a molecule in the lowest energy conformation is much higher than measuring current through a higher twisted conformation. So on average, we tend to get much more electrons going through geometry that is optimized at room temperature, just because these torsional rotations also have an energy cost.
Yeah. So right. So essentially, your calculations actually show that there is a single minima. Is it actually that for the
you can do calculations as a function of the torsion angle,
right?
And you get an energy for that, and it's about 0.3, 0.25 eV, something like that for these rotations. And that's enough to make sure that most of my electrons go closer to an energy minimized structure than a twisted structure.
Yeah, it's just also, Latha, have you really tried few things like hydrogen bonding between the chromophores? Like, for example, to fix the orientation, like you could have, these tricks where you can not just have a non-covalent hydrogen bonding interaction to allow for a more planar geometry.
Yeah, I mean, doing a fluorine compared to biphenyl is already, it's locking completely the conformation.
Yeah. Okay.
Yeah, and we've done this detailed study with biphenyl with different torsion angle, and we can map out the cosine squared dependence.
Okay.
And based on that, we know that for biphenyl, most of the time you're measuring close to the energy optimized structure.
Right.
But if you go to high temperature, where the rotations now become more and more probable, where twisted conformations become more probable, you should start to see deviations.
Right. No, and the other good part of this molecule, the trick was just you have a very strong accepting unit at the middle, which is localized, and then you can just work with the homos.
Yes.
The homo.
And the other trick is that as you get longer, the occupied orbitals all energetically get very close together.
Yeah.
And so HOMO and HOMO -1 are so close that I have to consider both of them, and the interference is critical.
Right.
If the energy level spacing between HOMO and HOMO -1 was large, which you have for short molecules,
right,
then you don't have to worry so much about that destructive interference.
Right.
And so there's two pieces. One is that LUMO is eliminated. The second is that these four orbitals are all so close together that we have to keep all of them in the picture. And the reason they're close together is because we have a long molecule. As your molecule gets longer and longer, your orbitals all the energy level spacing gets smaller. Okay, so we measured this molecule, and we measured it from a solution. Because the transmission is actually really low at Fermi, we had to apply a very large bias to do the measurement. And you can see, again, this is my standard cartoon, that, but now if you look at this nanometer scale, this is about 6 nanometers. Okay, this plateau extends to 6 nanometers. This is the longest molecule we have measured in the lab, and this is still coherent transport. And so this is a single trace. We can do an overlay of 3,000 traces. You can see that your 2D histogram extends 6 nanometers. Now, if I go back to the very first slide that I showed you, where IBM had made a 7 nanometer device, actually Apple now has a 5 nanometer device, and this is a 6 nanometer device. And so clearly we are beyond what silicon has done in terms of actually saying that we can measure molecules that are comparable length to, and this is crazy. I mean, this is amazing that you can get transmission across a 6 nanometer molecule. And when we, the referee reports for this paper, it was shocking because everybody, I mean, the referees were all saying, oh, this has to be hopping transport, because there's this concept that hopping is related to length. Hopping is not related to length. Hopping is related to the ability for the electron to occupy a state on the molecule. If there's no state for the electron to occupy, you cannot hop. And so that is the key aspect that you want to keep in mind. Okay, so now we want to test the nonlinearity of the transmission. So I showed you the transmission curve and I've explained the interference effect. So the nonlinearity, in order to test it, what we did is we hold the molecular junction and we applied the switching bias pulse. So we go between 0.5 volt to 2 volts across the molecule. So 2 volts is a lot of bias. And what you find is that the current goes from, this is our noise floor, so we can't measure this molecule at 0.5 because destructive interference really kills transmission. And then when you turn up the bias, you're opening your bias window, you're getting closer to your orbitals, you can see more than 0.1 microamps. And this axis, I mean, this increase in current is massive. We have never seen such a switching in a molecule. And so you can do this over and over again. And this is an overlay of 1,000 traces where we've done the switching experiment. You can see there's a few traces that sort of break, but most of them, they switch back and forth really reproducibly. And this is, again, a 6 nanometer long molecule. Okay, so that is the punchline. I should just acknowledge a bunch of people in my group, Suman here, Julia, who have done the last bit of the measurement, and also a lot of thinking about this Fabry-Perot analogy and all of that. And a few others and my collaborators. I just put everybody on the slide this way I don't forget to thank anybody. But you can look out for a new paper in Nano Letters with Satish's molecule that really talks about these conformational degrees of freedom. And I will end here. Yeah. And maybe stop with this figure.
Sure, sure. Absolutely fantastic. Thanks, Latha. Satish.
Yeah. Thank you very much.
This is wonderful. This is wonderful. And I think Satish will take some questions. There are still some questions. We will just take them first. In the chat box, Krishna Priya has asked, is it possible for a strong electrode molecule pair to cause conformational change in the molecule so that the conductance is affected by the change in rotational or vibrational degrees of the freedom?
Yeah, and this is something that we see, again, I will ask you to read this new paper that will come out in a couple of weeks or so. It really goes into what happens when you have conformational changes in the molecule with a diketoperoleoperol dimer molecule.
Right. Yeah, fantastic. Ravinder Kumar is asking, there are 3 linkers in this molecule. Do you consider both types of connections, like connections across? I guess what he's asking is, if you look at the structure of the molecule. Yeah.
Yeah. Why are there 3 linkers?
I guess what he means is the 2 sulfurs, and he's probably also thinking that the acceptor at the middle could link with the electrode.
Yeah, so actually the acceptor doesn't bind, and we've done control measurements without the terminal linker, and we see nothing.
Right.
And so this BT unit actually doesn't bind to gold.
Okay. Then there is Atindra Pal. What is the temperature dependence of conductance? Have you ever checked at low temperature? I can understand gold motion will be frozen. Will this affect the quantum interference?
So interference is very robust. It's not dependent on the temperature. Again, this is ballistic transport. It's temperature independent. The molecular orbital structure don't change whether you go at 4 Kelvin or room temperature. And so all of that is very robust. So you should see exactly the same effect at low temperatures.
Okay, Jayashree, Dr. Jayashree Nagesh wants to unmute herself and ask a question. Jayashree, please, could you ask the question? She's a panelist. Yeah.
Yeah, hi, thanks for a nice talk. So I had a couple of questions. One is, could you comment on the sort of magnitude of coupling between the, electrode and the molecule? What sort of coupling should we think about?
I mean, how can I think about,
so is it something
if
like,
I look at the width of the resonance, that gives you a magnitude of the coupling. And you can say here that it's, I don't know, milli EV, something like that.
I see.
We actually do a tight binding analysis to model the system. And there we have a better idea of what the coupling is. And I think, again, this paper will be published on Monday. We have a diagram that shows the coupling. I just don't remember. Maybe I can pull it up.
That's fine. That's fine. And another quick question is, so I think this sort of nice molecular orbital description is something, as you said, will work for, say, even neutral, charged, it doesn't matter. But what about for cases where you don't have even number of electrons? So let's say you have some open shell systems where, clearly you may have to go beyond the orbital sort of picture and invoke like, multiple multi-configuration kind of states, right?
Yes.
So how do you think about that?
Yeah, so for example, Blatter radical is one that we have looked at. There you have a nice singly occupied or a SOMO. And you can, again, think about whatever the alpha orbitals and just blindly follow this. But I think you have to start to be careful. This is really a model. So and it's a model that makes it easy to understand interference effects.
Correct.
But you shouldn't push your model beyond its applicability.
Yeah. Do you see the way it doesn't explain certain data because of the simplicity in those systems, like, the open shell case where some of your...
Yeah, actually for the Blatter, what we found is that it actually oxidized and became a regular a closed shell molecule in our measurement. And I think what happens is as soon as you trap it in the junction, you pick up an electron from the lead.
I see.
And then you have a closed shell system.
I see. Okay. Okay, thanks. Yeah.
Okay, well, I guess I will stop here because I guess Latha is she has already given us 1 hour, 45 minutes of our time, and this is, she has a meeting. We will stop here, Latha. Thank you very much. And I would like all my panelists to at least unmute themselves and give a big round of applause for this wonderful talk, absolute tutorial style. And I really think that you have set another benchmark for this webinar series. I think this was, of course, done all in one talk, unfortunately, but I think it was wonderful because you went through and through with the concepts and developed. I've never heard that comparison to the transmission problem in the optical cavity. So I think that was very nicely done. Thank you for doing that.
Actually, there's a paper from 1990s that does this in Nature, actually.
Okay. Fantastic.
Thank you. Fantastic. Thank you, Latha. Thank you.
Mm-hmm.
Thank you. So I will actually officially close this session by thanking all of you for coming and joining us for this session. And we will meet again in January with Professor Mikkel, who is an expert in singlet fission, who's going to give us 2 tutorial style talks exactly like.
Oh, Joseph Mikkel.
Yeah, Joseph Mikkel. Yeah.
You can say hi to him from me.
Absolutely, absolutely. We'll do that.
I didn't talk about his model. That's
Okay.
the one thing I skipped. But anyway.
Okay.
Okay.
Thank
Bye.
you.
Bye. Have a good day. Bye-bye.
Bye, guys.